Assalamualaikum and good afternoon. We are from group KK13. We'll be presenting on the monetization of POME into dimethyl carbonate from the production of methane gas. My name is WILDANI and I shall start our presentation with the project summary of DMC production from POME. First of all, the dimethyl carbonate, or also DMC, has a molecular structure of C3H6O3 with a boiling point and melting point of 90.35 degrees Celsius and 4.65 degrees Celsius respectively. It has a molecular weight of 90.08 gram per mole. And DMC is most commonly used as a solvent, reactive intermediate, and electronic materials such as in lithium-ion batteries. As for the profitability analysis, we received about 36,000 kg per hour of POME that is produced from feed rates of 60,000 kg per hour of fresh fruit punch. As for production, we will be using only 27,000 kg per hour of the POME. So the plant capacity that is calculated is 4.33 kilotons per year, with a global demand of 185,000 tons and global supply of 929,000 metric tons that is reported in 2016. So it will increase with a CAGR of 5.09% annually. As for general input-output process for this DMC, we'll be using POME, water, aniline and carbon dioxide as the raw material to produce DMC. And from this production, the plant will be generate waste gas and wastewater, but the purge gas will be using as a fuel source for the furnace F101. The next slide will be presenting by my other group members.
I will present the list of improved work based on the previous comment. Basically, in general, we updated the PFD and PID for the system and updated the stream table. Recycle of the discharge effluent of anaerobic digester AD back to the inlet digester for pH adjust instead of using raw POME. For conceptual design, we updated the overall DMC production, modify the FEV4, select the suitable sizing for each separation unit based on the annual costing. For heat integration, we updated the latest naming equipment and performed the new heat cascade and new temperature. For process control, we include all the figure of the control system in the report. This is the reaction condition of each stream, set point, manipulated variable, and control variable. For waste management, we added the stream table for the wastewater treatment PFD and included the BOD and COD reduction for each of process unit in wastewater treatment. For economic analysis, we checked the break-even analysis, ROI, and NPV. For plant location, we updated the latest plant image and updated the plant layout. And lastly, for safety, we include all the hazardous material, especially for the product hazard and safety. Next, the slide will be presented by my group mate. Thank you.
To find the best process flowsheet and to further optimize the design, we've done the conceptual design. We start out with a feed of 27 tons per hour for 24 hours each day of POME. We then flow that feed into our acidification tank, which has a retention time of 1 day using Clostridium acetobutylicum. Following that, we use an anaerobic digester, in which we have 4, with a retention time of 10 days using Methanocyanata conchili, which will produce hydrogen sulfide as a byproduct, so we must separate that. For that purpose, we use a biofilter with a bioscrubber, which will aid in the continuous removal of H2S. We then flow that into our first reactor, which is the R101, which is for dry reforming, which turns our methane into syngas. After that, we use R102, which is our methanol producing reactor, with our following parameters. After that, we have to separate the unreacted methanol and other gases. So we use a phase separator V101, which is a flash drum. After the gas has been separated, we flow that into our main reactor, R103, which is our DMC producing reactor, which has the following parameters. So to further purify the product, we first flow it into a flash drum, V102, which separates the unreacted CO2. After that, we have to further purify it because it's our main product. We use a extractive distillation, which we must use as our methanol is an azeotropic mixture with so we have to use an entrainer aniline, which aids in the separation. After that, we have to separate the aniline from the mixture. So we use a recovery distillation column, D102, which will purify our product as well as recollect our aniline.
Here, I'll be explaining on heat integration. Heat integration can lead to a substantial reduction in energy requirement of a process. Pinch technology is one of the most successful and generally used techniques. We applied problem table method to identify the pinch temperature. Considering all 12 hot utilities and 2 cold utilities, after performing all the calculations, we're considering that stream 32, 32A and 32B has been integrated by adding 2 heat exchangers. And by comparing both energy required before and after HI, the total energy has been successfully recovered at 31.71%. Next, I'll hand in to my teammate for the next presentation.
This chapter is discussing the control system that monitors the operations of every unit in our plant. Firstly, I will introduce the control configurations of an anaerobic digester. The first controller is pH controller. It is used to maintain the pH level between 6 to 8, while the second controller is used to control the operating pressures and safety levels. Followed by the control configurations of 3 main reactors in our plants. They are operated at high temperature. Hence, temperature controller is used to prevent overheating inside the reactor. Besides, the pressure controller is used to avoid overpressure conditions in the reactor. Next, there are 2 flash separators along with 2 controllers in our plants. The pressure controller has been used to control the pressure inside the vessel to prevent overpressure, while the level controller has been used to control the liquid level inside the vessel to prevent overflow. The screen shows the control configurations of extractive distillation column D101s. Among 4 controllers at D101s, flow ratio controllers have been used to control the flow rate of anilines into the columns by regulating the flow rates of raw anilines. Lastly, similar as the control configurations of previous unit D101s, at D102, the composition controller is used to ensure the purities of DMC reach about 97%. As screen shown is the piping and instrumentation diagram for our plant, and the next part will be presented by my groupmate. Thank you.
For wastewater management, refer to the activity and action required to manage the waste from its inception to its final disposal. For it intended to reduce the adverse effect of the waste on human health and the environment aesthetic. Basically, in our plant, the waste gas produced from the flash separator V101, we are using the excess gas or purging gas as a fuel in furnace F101. The waste gas composition is carbon monoxide, carbon dioxide, hydrogen, methane gas, and trace amount of ammonia and hydrogen sulfide. The effective stack height is calculated based on the Holland equation, and the effective stack height is 164 meters. The waste gas from the furnace is sent to the flare before released to the environment. For liquid treatment, is divided into 2 treatments, which is primary and secondary treatment. The waste gas is produced from the anaerobic digested tank and biofilter. We are using activated sludge process in our process. The inlet BOD is 3,585 mg per liter, COD 7,117 mg per liter, and total suspended cell is 7,500 mg per liter. There are 3 aeration tank, which is our primary treatment, has BOD reduction of 82.57% and COD reduction of 78.46%. For clarifier, the TSS reduction is 99.35%. solid waste is moved to the filter press for further separation the solid and liquid. The solid waste from the filter press is used for composting. The discharge water is compared to the standard air, which has COD of 73.18 mg per liter and BOD of 19 mg per liter, compared to standard air with COD of and BOD of 120 and 20 mg per liter respectively. Thus, the COD and BOD not exceeded the limit of standard air. Next, I will pass to my other teammate to present their part. Thank you.
Next, for plant location, we have choose Jalan Bidor Lama, Tapa, Perak as our plant location. It will be located beside Cahaya Muda Palm Oil Sdn Bhd, which produces 525,000 tons per year of FFP, providing sufficient POME source for our plant. It is a very strategical location, convenience of facilities, river for discharge, and also a good marketing area. Now let's look into our plant layout. Plant layout gives us an overall concrete view of arrangement of process and ancillary buildings. Inherent safety are important in mitigation of hazard. First, a good plant layout will greatly reduce potential hazards. There are a few aspects that we could look into. First, the ancillary building that involves high concentration of human activities are located far away from the reaction region. Second, there are 3 assembly areas and 3 exits for rapid evacuation during emergency. Third, feed and product storage are located beside reaction region to ease the supply and collection. 4. Workshop, cooling tower, and compressor room are located near the reaction region to provide utility and support for the main reaction. 5th, the control room, located at the corner of production plant, enable a good overview of the plant. High temperature reaction region are protected with firewall to prevent accidents occur. Arrangement of unit near the roadside is to ease the maintenance work. 6. Cooling point located furthest away from the human activities to reduce odor and high temperature POME. 7. Firehouse located at the reaction region to ensure ERP can be executed in shortest time during emergency. Lastly, wastewater that are treated and discharged to Sungai Batam. As for gas treatment, it is located near the southeast corner to ensure safe purging of gas along with the wind direction. Next, I'll hand in to my teammate for the following presentation.
Profitability analysis is carried out by 2 methods, which are the methods that do not consider the time value of money and the methods that consider the time value of money. In these chapters, returns on investments, payback period, and net returns are calculated to evaluate profitability of the project. The chart shown in screen depicts the net cash flows over 20 years of operations. ROI of this project has been calculated as 3.81, while the payback period is approximate to 4 years. Besides, the net present value of this project is equal to 369.95 million ringgit with DCFRR of 33.6%. And the next part will be presented by my good man. Thank you.
For the safety analysis, since the production of TMC is using hazardous chemicals and also operating at high temperature and pressure, so any source of hazard must be identified in order to prevent any accident and incident from occurring at workplace. Therefore, we must obey the legal requirements and acts that place a general duty to ensure the health, safety, and also welfare of the employees. So the major acts that involved are the Safety, Health and Welfare at Work Act 2005. So this act is actually about the transportation hazards that exist in the workplace. They must be assessed as part of the risk assessment and appropriate steps taken to eliminate or reduce any risk found. So as the DMC production will be using aniline and also carbon dioxide as the feed. So this aniline is purchased from the outside to be used in the extractive distillation column. Therefore, the safe transport hazard is needed to prevent the accident from happening. Next is the Occupational Safety and Health Act 1926 of Safety and Health Regulation for Construction. So this is regarding the flammable liquid, which stated that not more than 25 gallons of flammable or combustible liquid may be stored in a room outside of an approved storage cabinet, or also not more than 60 gallons or 120 gallons of combustible with the flash point of below than 140 degrees Fahrenheit may be stored in any one storage cabinet. So for our plant, we have the DMC, which is a flammable liquid with a flash point of 17 degrees Celsius. So we need a safe work environment where it will be stored in an airtight closed container. Next is the OSHA 1994 of Control of Industrial Major Hazard, Regulation 1996. This regulation is to mitigate the consequence of major accident in a workplace. So for our product, DMC will be stored in an airtight closed container. So for this container, we must obey the storage capacity of product, where we store only 700 tons of dimethyl carbonate into the containers or the storage tank. For hazard identification, we have identified 5 chemicals that is considered as hazardous in the DMC production plant. First is the hydrogen sulfide, which the flammability is classified as 4, as well as the health, because it is rapidly or completely vaporized under normal temperature and pressure, and if it released to the environment, it can cause death or serious residual injuries, but the reactivity is normally stable. For the hydrogen gas, it may react violently with oxidizers and form mixtures with air, which leads to flammability or explosion. For methane gas, it is normally stable and not reactive with water, and if exposed under fire, it will not offer any harm. However, it can rapidly or completely vaporize at normal temperature and pressure, so it is a flammable gas. For methanol, the flammability is classified as 3 and the health is 2, because it can be ignited under almost all ambient temperature conditions, and also it can cause temporary incapacitation or residual injury under the emergency condition. For the dimethyl carbonate, it can form an explosive mixture with air and also travel the source of ignition and flashback. Also, it may cause explosion in contact with the heat, so it is considered as the flammable gas as well. And the hazard analysis will be presented by SHARVINI.
So this is the hazard for syngas reactor. When the temperature is really low, it's going to cause a lower rate of reaction. This is mainly because of the inlet reactant temperature, as well as the furnace and heat exchanger malfunction. And the safeguard installation we have got here is that we have got a temperature controller as well as a low temperature alarm. And when the temperature is really high, it's going to cause the reactor to rupture and to release hazardous gases. And we have a cooling water jacket as well as a rupture disc inside the reactor itself. Secondly is for the methanol reactor. When the pressure is really low, it's going to cause production of off-spec product which does not meet the requirement. And this is being added on with an emergency shutdown system which can be triggered by low pressure indication by the pressure controller as well as an alarm. And when the pressure is really high, it's going to cause explosion, and this is going to lead to increased number of major injuries and fatalities. And we have got an explosion suppression system which contains blast wall as a safeguard system. Next is the hierarchy analysis for the syngas production, and the main hazard scenario involved here is the valve malfunction as well as the pipe leakage. And the additional control measures for this is actually the field mud detection system as well as the dike to contain this field. Since it's going to be exposed to flammable source, we need to use an explosion proof system as well as blast walls around the unit. And we have a process containment system which has a floating roof tank to eliminate toxic vapors when the reactor gets overpressurized. And additionally, we have mechanical fuse which act as a low link designation, which will actually melt when the pressure exceeds its limit. And since it's operating at a very high temperature, we have a sprinkler system to distinguish if there's any firing occurs. Lastly is the process and instrumentation diagram. We have actually reconstructed it after analyzing the HAZOP detailing. So for this, we have actually added on alarms to all the major unit operation. For instance, we have added on a pressure alarm as well as temperature alarm to the syngas reactor, as well as a level alarm to the phase separator.
I will present the biofilter part for individual design. For biofilter, it's used to eliminate the hydrogen sulfide from the gas mixture. We are using the bacteria as a catalyst to absorb the H2S. Operating condition for biofilter is 35 degrees Celsius. The fourth table below shows the parameter of each inlet and outlet of the stream for the biofilter. Gas flow rate entering the biofilter is 1621 kg per hour with temperature of 35 degrees Celsius and operating pressure at 1 bar. The pollutant for the waste gas is hydrogen sulfide. For column sizing, the diameter of the biofilter is 1.5 meter with height of 6 meter respectively. For the design pressure is 2.6 bar and MAWP vessel is 2.2 bar. Because of the MAWP vessel is much lesser than design pressure, which is 2.6 bar, and MAWP vessel is larger than the operating pressure which is 1 bar, thus the design is safe. For material construction, we are using the stainless steel SS316 with type of support of skirt support and support material of carbon steel SA516. Type of flange used for joint is welding neck flange. For stress analysis, because of the maximum allowable stress is much lesser than design stress, thus the design for the biofilter is safe. And for elastic stability analysis, the compressive stress is much lesser than critical bulking stress, thus the design is safe. Next, I will pass to my group mate for next presentation. Thank you.
This slide is about the detailed designs of reactor R102. This reactor is operated at 213 degrees Celsius and 80 bars to convert the syngas into methanol. It is a multi-tubular reactor with short and tube heat exchangers arrangements. The catalyst copper zinc aluminas are embedded in tubes where the reactant gas will pass through, while the cooling waters will be circulated at the shaft side to remove excessive heat produced. From process design level 3, the reactor volume is determined as 9.78 meter cubes for 80% conversions. There are 980 tubes inside the reactor with lengths of 6 meters. By assuming 5% additional length at top and bottoms of the reactors, the total length is equal to 6.6 meters. Since the temperature difference inside the reactor is very small, hence the calculator's overall heat transfer coefficient is very small. Based on the chemical use and operating conditions, the construction materials of this reactor is austenitic stainless steel type 316 SH240. The vessel height is equal to 7.682 meters. The minimum thickness of this vessel is 88 mm, while internal and external diameters of the reactors are equal to 2.163 meters and 2.339 meters respectively. The minimum allowable working pressure is found to be 91.63 bar. As screenshot is the mechanical drawing of reactor R102, and the next part will be presented by my groupmate. Thank you.
For the heat exchanger E103, it is used to cool down the methanol product and residue gas from 117.2 degrees Celsius to 40 degrees Celsius. It also used to reduce the pressure of 80 bar to 40 bar. And then the cooling stream is assigned at the tube side, while the methanol product is at the shell side, and the flow is a countercurrent flow. For the detailed design of heat exchanger E103, the flow rate at the shell side is 1964 kg per hour, while the tube side is 1813 kg per hour. The outside diameter is chosen as 0.016 meter with the wall thickness of 0.0017 meter. And the length of tube is 4.83 meters. So the number of tubes is 1158 tubes. The buffer cut is taken as 25%, therefore it gives the buffer spacing of 0.133 meters. The tube side pressure drop and the shell side pressure drop is 2.98 psi and 1.35 psi respectively. For the mechanical design, the material construction for the heat exchanger is taken as stainless steel SA240 grade 316. The design pressure for this heat exchanger is 856.12 psi, with the internal vessel diameter of 0.442 meters and also the shell height of 2.415 meters. And the MAWP vessel is 643.49 psi. So you can see that the comparison of MAWP vessel and also the design pressure, the MAWP vessel is smaller than the design pressure.
Phase separator V101 was designed by me. It is a flash drum which operates at 120 degrees Celsius at 80 bars. It functions to separate the carbon dioxide and other gases from water and methanol. This flash drum is assisted by a deflector plate which supplements in the disengagement and a mist collector for trapping evaporated water and methanol. For the detailed design of V101, it has a liquid mass flow rate of 1507.61 kg per hour and a vapor mass flow rate of 457.02 kg per hour. It has a volume of 4.45 cubic meters and a minimum vessel diameter of 0.038. The liquid depth of the vessel is 0.12 meters and it has a hold-up time of 10 minutes. The disengagement height is set for 0.92 meters and has a total height of 1.742 meters. Moving on to the mechanical design of the phase separator V101. On the left hand side you will see the mechanical drawing done by me, and on the right hand side you will see all the specifications. It has an internal diameter of 1.156 and an external diameter of 1.241 meter. It has a minimum thickness of 0.042, and we're also using a hemispherical head for the bottom and the top. It has a cylindrical shell height of 0.552, and based on the thickness it has an MAWP of 6.834 Newton per millimeter squared. It has an elastic stability of 0.181, and it also has 8 bolts for the base ring. The bolt root diameter is 1.241, and the area of one bolt is 7.319 millimeter squared. The thickness of the base ring is set for 0.04.
So next would be the detailed designing of a reboiler, which was designed by me. So here we have actually used a cathode reboiler which is used to heat up the distillate from the extractive distillation column, which consists of aniline, methanol as well as dimethyl carbonate. So the distillate here, it is heated up until 185 degrees Celsius, which completely vaporizes all the components inside the distillate. So we have used hot steam as our heating agent, which has a temperature of 200 degrees Celsius. And this particular reboiler has 62 tubes, which has an area of 0.307 meter per square. It has a fluid velocity of 1.38 meter per second in the tube side and 0.0398 meter per second in the shell side. and we have used double split flow shell here. And moving on to the mechanical design, we have used SA216 carbon steel as the material of construction with a length of shell of 6 meter with an inside diameter of cylindrical shell of 0.8 meter with an ellipsoidal and length of 2.03 meter. And this particular reboiler has a calculated design pressure of 15.95 psi with a maximum allowable working pressure of 399.20 psi with a corrosive allowance of 0.02 meter. And this uses a vessel support of saddle and a welding neck flange which is made up of 200 BS1560 carbon steel. And that's all from me. Thank you. Next will be proceeded by my team member.
For the individual design, I'll be introducing distillation column D102 that separates our product DMC from aniline. Due to the difference in boiling point, DMC will be vaporized as a top product and distillate to form a final product, while the aniline are recycled back to the first distillation column. The feed enters the distillation column at 130 degrees Celsius and 2 bar. Detailed calculation is performed on D102 with a reflux ratio of 1.226 and minimum of 13 stage is obtained. With the theoretical stages of 25 and efficiency of 66.38%, the actual number of distillation column is actually 39 stages, with a height of 25.116 meters and near to 3 meters of inner diameter. The tray spacing of 0.6 meter is used. The feed will be flowed at the 5th stage from top. I have performed mechanical design as well on D102. Stainless steel SS316 is chosen as a construction material due to the slight corrosivity of aniline. Ellipsoidal head is chosen for the design with 0.749 meters and shelf height of 23.62 meters is calculated. D102 will be having vessel nominal thickness of 8 mm considering corrosion allowance of 2 mm. After performing calculations, it can be identified that the MAWP vessel of D102 is 40.764 psi or 2.81 bar. As for the skirt, it will be carbon steel material with assumed skirt height of 3 meters. As for the base ring, 16 bolts are used with a diameter of 8.482 mm and base thickness of 17.663 mm. Welding neck flanges are used for all pipes and calculated pipe sizing are 2 inch for inlet pipe, 10 inch for top outlet pipe, and 1.5 inch for bottom outlet pipe as shown. Mechanical drawing are not drawn to scale, but it's referable.
As for the conclusion, with the operation of 350 days per year, the production capacity of this plant is 4.33 kilotons per year from POME feed rate of 36,000 kg per hour. The comparison of mass and energy balance is calculated with SuperPro and icon simulation gave a percentage of error less than 5%. And the total energy recovery is 32.21%, which is carried out from the heat integration. The estimated capital investment for this plant is 468.82 million ringgit with the product cost of 191.42 million ringgit per year. The return of investment is estimated as 3.81 years with a payback period of 3.95 years. The net present value is 369.95 million ringgit with the cash flow rate of return is 33.6%. So after the treatment of the wastewater, we have BOD and COD content of the effluent discharge are 19 milligram per liter and 73.17 milligram per liter respectively. And the detailed design of each unit and also the mechanical design is calculated based on the ASME code and TEMA ISO basis. So that's all from us. Thank you.